Hello everyone, welcome to BYJU'S Exam Prep, the most comprehensive preparation app for all exams. Good evening all of you. Am I properly audible and visible to all of you? Please confirm once in the chat box, guys. And guys, keep sharing this session, because this session is going to be really interesting. We are going to start operating system and the topic is Introduction to Synchronization. So those who are aiming for GATE 2023, don't miss this class and this entire series, because this is the most important topic in operating system and we are going to cover the concepts plus the questions. Good evening, Tushar. Yes guys, do share this class. Good evening guys. Yes, everyone, keep sharing and keep liking the session. We are going to start now. Good evening, Utkarsh. So guys, are you ready? Mastering GATE concepts, operating system, introduction to synchronization. Good evening, Rakesh. Yes guys, do like the session and share with your friends as much as you can in all the Telegram and WhatsApp groups. Good evening, Anu. Good evening, Shalini. Okay, so let's start introduction to synchronization. So before starting, let me introduce myself. My name is Anshul. I have 2+ years of experience, and in GATE 2020 I have secured All India rank 294, cleared ISRO and NILET exams, mentored more than 1,000 students as of now, and these are my area of expertise: operating system, digital logic, compiler design and computer organization. Good evening, Aisha. Okay guys, do like the session and share as much as you can. So guys, if you want to get the PDF of all my YouTube classes, so you can join this Telegram group. Okay, CS_by_Anshul_Sir. So you can join this and you can connect with me, because I will be sharing all the PDFs. You can ask your doubts there, and if you need any guidance, then also you are most welcome. Good evening, Unstoppable. Yes guys, keep sharing the session because we are going to cover this introduction to synchronization in detail. Everything we are going to cover here. Okay, then after attending these classes, you don't have to refer again any other lecture for this, I can tell you that. And there is one strategy to conquer GATE 2023 workshop, so you can attend this on 13th of March. Timing is 12:30 PM. So our dear Abhinav Negi sir will be taking this session, and if you have any doubt related to GATE 2023 preparation, what should be the strategy, everything you can discuss, you can ask to this Abhinav Negi sir, and he will be guiding you also. So guys, let's start without waiting. Process interaction. So first of all, in process synchronization unit, we are going to talk about process interaction, that is IPC, inter-process communication. IPC is nothing but inter-process communication. Inter-process communication. Okay, so in inter-process communication, first of all, we talk about two types of processes. Good evening, Robin. So we talk about two types of processes. So one we have is independent or isolated processes, and other one is your cooperating processes. So we have two types of processes. One is independent or isolated, and other one is your cooperating processes. Now what is this independent processes? The processes which are not dependent on each other. That means they are one process can perform its operation separately, another process can perform its operation separately. They are not sharing anything. They are not sharing anything among each other. So that is why they are separate. So we call those processes as independent processes. Now if I talk about cooperating processes, so basically one process can affect the result of another process also. So we can say they are sharing some. Yes, this is the first lecture of OS. Yes, Aisha. So in case of cooperating processes, one can impact the result of another process, and similarly vice versa is also possible. So we call those processes as cooperating processes, because they have something shared, you can say the shared memory or some shared resource that is going to be accessed by both the processes. That's why we call processes as cooperating processes. So as you can read here, it cannot affect or be affected by the execution of another process. That's why we call it as independent or isolated process. But if you talk about cooperating processes, it can affect the other process or be affected by the execution of another process. So those processes are cooperating processes. Is it clear so far? Two types of processes we have, independent and cooperating. Yes, noob, PDF will be available. I will be sharing the PDF in my Telegram group. Okay, so you can join that group and there you will be getting the PDF after this class. So let's proceed. Now there are two mechanisms. So basically whenever we talk about synchronization, we talk about cooperating processes, right? Because we need to maintain the synchronization between the processes which are affecting each other, okay, which are affecting or which are sharing something. So that is why we have two mechanisms here. One is your shared memory and other one is your message passing. So these are the two mechanisms we follow. We have one more, that is pipes, but now we don't use it. So we have shared memory. That means in case of shared memory, let's say we have two processes, let's say P1 is there and P2 is there, and we have one shared memory. So this P1 is also going to access the shared memory. Maybe you can have some resource, maybe you can have some common variable here in the shared memory, and this P2 can also access this. So we can have the communication between these two processes through shared memory, and it is faster than message passing. Now what is message passing? So basically we directly send the messages to one process to another process. I will tell you how. So basically we directly send the messages to through two methods. One is direct method and other one is indirect method. So in indirect method we send the messages through ports. So for every process we have the ports defined and we send the messages, or directly we can also send by specifying the process name and whatever message we want to send. So these are the two ways. Now if we talk about shared memory, that is faster than message passing. Why? Because message passing involves system calls. That means whenever system calls are there, OS intervention will be there. OS intervention will be there. Okay, that means kernel intervention is there. So that is why it makes it slow. This is slower. This is slower. But this message passing is useful for exchanging smaller amounts of data. So if you want to send from one process, if you want to send some data which is very small to another process, so you can use message passing, and it is easier to implement also as compared to shared memory. Is it clear to all of you so far? Now let's talk about shared memory. Let me give you one example also for shared memory and message passing here. So this is the real life example. As you can see, compiler is there. So compiler we can consider as the producer. So compiler generates the assembly code. We know this. Those who have studied compiler, then they might be knowing this. If not, then don't worry. Compiler generates the assembly code. So this assembly code will be consumed by your assembler. So we can say this is a consumer here. That means we are having some shared memory where it is producing and it is accessed by the consumer here. Similarly, assembler is going to generate the object modules, which is going to be linked by the linker, and it is going to be loaded into the memory by the loader. So here it is acting as a producer here, and this is acting as a consumer here. Clear? So we have the shared memory where we are going to share the, where we are going to send the update the memory, which is the shared memory, and here we are updating object modules, which is consumed by linker and then loader. What is kernel? So kernel, you can say the space where we have all the system services when we want to execute the system services. So OS intervention is required. So OS always execute those processes, those services in the kernel mode. That is kernel intervention. Is it clear, everyone, so far? Ports we defined for every process here. Like you can see here, for message passing we have two methods. So let me explain you. For message passing we have direct method, we have indirect method. Okay, when we talk about direct method, so directly we can use this these commands. So we have a P, we are dedicating P process and we are sending the message. Similarly, we have Q process and we are sending the message. But in case of indirect methods, we send the message to the ports defined for the processes. Clear? This is indirect message passing. So two types of message passing is there, direct and indirect. And if we talk about shared memory, so here a web server we have, when we open a web browser, we request, okay, just a minute. When we open a web browser, we request the web server to send the HTML pages, HTTP pages and images and files. So here it is acting as the producer, and we have some shared memory which is accessed by the web server, also by the web browser, to use those resources. Is it clear so far, everyone? So these are the mechanisms that we have. These are the mechanisms that we have in case of cooperating processes. Now let's proceed and let's talk about the main synchronization thing. No, in that case, in indirect it is not using. In indirect they just directly refer to the ports. Utkarsh. Now the point is, why do we need synchronization? Now this is very important. Why do we need synchronization between the processes, between the cooperating processes? The reason is to avoid data inconsistency. To avoid data inconsistency. Now how we can have data inconsistency? Yes. So now let me take one example and it will be clear to you, crystal clear to you. Let's say we have one process P1 and we have one process P2. Okay. Now in this process we have one statement which is like this, count plus plus, and here also in process P2 we have one statement written here, that is count minus minus. Okay, and then we have some other statements also. Here we have other statements also. Clear? Now as you can see, P1 and P2 both are accessing the common variable. So let's say we have count as the resource, the common resource, or you can say the common variable. Now let's assume that the initial value of count is, let's say, 4. Okay, initial value of count is 4 here. Now carefully observe, when this, let's say P1 is executing, we have allocated the CPU to P1 process and now P1 is executing. So when it is going to execute this statement count plus plus, now if we consider this statement at the assembly level instructions, at the shared variable, yes, it is shared variable. So at the, if we see at the low level code or assembly code, so here it is going to be something like this, load count comma R0. So let's say this process P1 is using one general purpose register which is R0, and here you have count. So what we are doing, we are going to load the value of count into R0. Clear? Then we are incrementing it count plus plus, so we have inc, that is the increment, and then here we are writing R0, so increment R0. Clear? Then we are going to store it. So we are going to store it back to count from R0. Is it clear? So at the assembly level you can see this count plus plus is nothing but these set of instructions. Is it clear, everyone, so far? Now let's talk about this count minus minus. Now here you can see it is going to be load count, let's say it is using R1. Okay, R1 is another general purpose register which is used by process P2. Now it is going to decrement it, so decrement R1, and then it is going to store it, store R1 comma count. So it is going to store back the updated value of R1 to count variable. Clear so far? Now the initial value of count is 4. Let's say P1 is executing. Let's say P1 is executing, and let's number these instructions as 1, 2 and 3. Okay, similarly let's update it as 1, 2 and 3. Now carefully observe, P1 is executing. Let's say P1 is executing the first instruction, load count into R0. So here in R0 we are going to have the value 4, yes or no? We are going to have the value 4. P1 and P2 are the processes. What is process? Program under execution. So you write one source program in C programming language. So program under execution becomes process. So here we have one process P1, we have one process P2. P1 is accessing count variable, which is a common resource. Take a common variable. Here it is updating the count value. Here it is decrementing the count value. Here it is incrementing, this is decrementing. So as we can see, this is a common or this is a shared resource. So I'm showing you here is how we can have, why we need synchronization between these two processes. So carefully listen this. Now in R0, P1 is executing, it has loaded the value of count into R0, fine. Now let's say it is incrementing, let's say it is executing its second statement. So if it is incrementing R0 value will become 5, yes or no? R0 value will become 5. Now carefully observe here, let's say this P1 process got preempted just after executing its second instruction. It got preempted. Now if it got preempted, let's say P2 is executing now. So what P2 will do? P2 will also load the value of count to R1, its general purpose register. Still the value of count is 4 only. Fine. So here this R1 value for P2, it is going to be 4. Now let's say it is decrementing. So if it is decrementing, it will make the value 3. Fine. Now let's say it is storing the value. So R1 to count. So if it stores the value R1 into count, what do we get? So we can say, we can directly update here, the 4 value will become 3. Clear? So P2 process has updated the value of count from 4 to 3. Clear? Now let's say after complete execution of P2, P1 got the CPU back again and now it is executing its third instruction. So what it will do? In its register, general purpose register, it is having the value 5. So what it will do? It will update it by 5. Now what is the problem here? The problem is, let's say after this P2 is also having some other instructions where it is going to use this count value. So what will happen? In that case? In that case, P2 is going to read the incorrect value, because for P2 the correct value, the updated value should be 3. But what it is getting? It is getting 5. Are you getting this point, everyone? Good evening, AB. Is it clear so far? So then why we use scheduling? We can schedule them. See, we use scheduling so that we can arrange the process execution. But the point is, when we are executing P1, like we talk about round robin, so we preempt the process, right? We preempt the process. Let's say some P1 process wants to perform some input output operation, right? In that case, CPU will be allocated to another process. So this is happening here. In between that preemption, this is happening here. Is it clear, everyone? Okay, that's why we need synchronization, because in this case we are going to have the data inconsistency. The one process will be reading the incorrect value if it is sharing some common variable, some common resource with other processes. Is it clear so far? Please let me know this. Exactly. Yes, Shailesh, that is correct. Why we perform this increment and decrement value? What is the logic behind this? Here I am explaining you why do we need synchronization. So I have considered this case where P1 is incrementing count plus plus and P2 is decrementing count, that is count minus minus. So here I am explaining you how we can have the data inconsistency. What is the problem? Why do we need synchronization? Is it clear, Utkarsh? Okay. So this is the problem. Now to resolve this problem, we need some solution also, right? So let's talk about the solutions. So we have some basic definition. Let's first go through the basic definitions and then I will be explaining you what are the synchronization mechanisms and what are its conditions. So first let's go through these basic definitions. So the first definition we have is atomic operation. So what is atomic operation? Execute all or none. Execute all or none. It's assumption. So you can take other cases also where two processes are sharing some common resource, right? In that case also we can have data inconsistency. Here I have taken one example so that I can explain you how we are having that inconsistency. Is it clear? Yes, it is assumption. Okay, but it happens. So let's talk about atomic operation. Atomic operation means execute all or none. That means if you have certain operation, let's say count plus plus, in count plus plus, if you are having load first, then increment, then store. So if you want to execute that load operation, so that should be what? That should be atomic. Okay, indivisible operations. Yes, you can say, Anu, that is correct. Clear? So you can read here a sequence of one or more statements. So we can make more statements, more than one statements also as your atomic operation. That means if I want 3 instructions to be executed without any preemption, so it will be executing complete instruction, or it is not going to execute that. That is atomicity. So a sequence of one or more statements that appears to be indivisible, that is, no process will interrupt the operation. That is atomic operations. Is it clear? Is it clear to all of you so far? Now let's talk about the second definition. Now in the previous example that I have discussed between P1 and P2, and we have the count variable, that is a common resource, common variable. So if we have some resource which is present, which we have some shared resource which is being accessed by 2 processes, let's say P1, P2, or more than 2 also, so that area of code we call it as critical section. So here you can see a section of code within a process that requires access to be shared resources, and that must not be executed while another process is in a corresponding section of code. So like here you can see here, we can say in this one we can say that this section of code is nothing but our critical section. Similarly, this piece of code, this is nothing but our critical section. Why? Because in this P1 process, in this code, we are going to access this common or shared resource which is also being accessed by other process. So this piece of code we call it as critical section. So at a time we want that only one process should be able to access the critical section so that we can avoid the data inconsistency. Is it clear? Is it clear to all of you? If you have any doubt, please ask. Anyone? Okay. Right. So now let's see some other definitions as well. Now what is a deadlock? What is a deadlock? So a deadlock is a kind of situation where one process is waiting for another process or waiting for another resource which is being held by some other process. Let's say we have one process P1, we have one process P2. Let's say P1 is in need of resource R1. Okay, it is waiting for R1 which is being accessed by P2. Similarly, P2 is waiting for resource R2 which is being currently accessed by P1. So what is happening here? P1 is not releasing R2 because P2 needs that, and P2 is not releasing R1 and P1 needs that. So ultimately both are waiting for each other to perform certain operation, but they are unable to do so. So that situation we call it as a deadlock. That situation we call it as deadlock when there is no progress. Basically, when there is no progress, we can call that situation as deadlock. So whenever there will be a deadlock, there will be no progress. You can clearly say this. Okay, remember this point. So a situation in which 2 or more processes are unable to proceed because each is waiting for one of the others to do something but they are not doing. Clear? So that is a situation of deadlock. If you have any doubt, guys, so far, please ask. Please ask. And if everything is clear so far, please let me know also. Now let's talk about 2 more definitions which is also important here. That is race condition. Race condition. Now what is race condition? So in that same example that we have covered, P1, P2 and count variable is a common resource, shared resource. So in that case, what will happen? The final result of count will be decided by the order of process execution. Let's say P1 is executing, right? It is updating the value, and then later on P2 is updating the value. So final result will be depending upon the order of process execution, and this situation, this condition, we call it as race condition, because ultimately you can see here the final result depends on the relative timing of their execution, whether P1 is executing first or P2 is executing first, whether P1 is updating the value first or P2 is updating the value first. So that will be, yes, there is a race between the processes to access the shared variable, exactly. Okay, so this is what we call as race condition. Is it clear so far, everyone? Now let's talk about starvation. So what is starvation? Starvation is basically a situation. Let's say there are two guys and both are hungry, okay, and let's say one has started eating, right, and other one is waiting, okay. Now after some time, when let's say the person B was thinking like, okay, now it's my time to eat some food, to have it, and then I can do some other work. Then at that time again the person A will again get the food, and he is not allowing the process B, he is not allowing the person B to access that food. So basically in that case person B will face starvation, right? Exactly. So here starvation is, you can say, a situation in which a runnable process is overlooked indefinitely. That means you don't know the time. You don't know the time by the scheduler. Although it is able to proceed, it is never chosen. So the scheduler is not going to choose that process. In that case, that process will face starvation. Okay. So in simple terms, we can say starvation is nothing but indefinite waiting. Or you can say long time waiting, because we are not certain when we are going to get the chance. Okay, so starvation is indefinite waiting or long time waiting, and whereas your deadlock is nothing but your infinite waiting. Is it clear to all of you? Everyone? Okay. So these are the basic definitions that must be clear before proceeding to synchronization mechanisms. Okay, so now let's talk about the conditions for synchronization mechanism. Now you have seen how we can have data inconsistency. Now if someone is proposing a synchronization solution, then there should be some criteria, there should be some conditions that should be satisfied. Then only we can say, okay, you have proposed one solution for synchronization and it is satisfying these requirements. That means your solution is good. We can adapt it. Yes or no? So there are some certain conditions, and let's talk about that. So the first condition we have is mutual exclusion. I will explain you each and everything, guys. Keep sharing and keep liking the session. Second condition we have is progress. Third condition we have is bounded waiting. And the last but not the least, the fourth condition is your architectural neutrality, or you can say architectural neutral. So these are the four conditions that need to be satisfied if you are proposing any synchronization solution. Now let's talk about it one by one. What is actually mutual exclusion? Mutual exclusion means no more than one process should be able to access the critical section at a time, or you can say simultaneously. That means at a time you should allow only one process to access the critical section. Critical section means where you have the shared resource. So you have process P1, you have process P2, but at a time you are just allowing only one process to access that critical section and then perform its execution. Then after that you are allowing other process to access the critical section. So At a time, only one process should be able to access the critical section. That is nothing but your mutual exclusion. Is it clear? Is it clear? Any doubt so far? Anyone? Okay. So no more than one process should be able to enter into the critical section. We can say yes, mutual exclusion is satisfied. Second is progress. Now to explain you the progress, let me take one case. Let's say there is one park. Okay, and it is full of grasses, right? There is one dog and there is one horse. Now this dog, it doesn't want to enter into this park. Okay, it doesn't want to enter into this park. It is not interested to access this park. Okay, but this horse, it is interested to access this park and eat all the grass it has. Clear? It is waiting for that opportunity. Okay, it is interested. Now what this dog is doing, it is not allowing this horse to enter into this park and access this grass. So dog is stopping the horse to access this park and to eat all the grass. So that means progress is not there. Because let's say now you have process P1. Let's compare this with process P2. Let's say you have this critical section. P1 is not at all interested to access this critical section, but P2 is interested. So but this P1 process is not allowing P2 to access into the critical section. If this is the case, we can say progress is not there. That means let's say we have one room, okay, and there are two guys. One wants to enter into that room, other is not allowing, other is not interested, and even he is not interested, still he is not allowing the other guy to enter into the room. So that means he is stopping the progress. He is not allowing the other process to access the critical section. Is it clear to all of you, everyone, what is progress? That means in case of progress, other process should not be interested. Only one process, let's say it is interested, but it is not able to access the critical section because the first process is stopping that, is not allowing that process to access the critical section. Is it clear, everyone? If you have any doubt so far, please ask. Anyone having any doubt? So this is what we call as progress. Now let's talk about bounded waiting. Here. Bounded waiting means there should be some limit on the number of times a process can access the critical section, right? Let's say you have one process P1 and you have one process P2. Let's say this is your critical section. Let's say P1 is accessing that. Okay, it comes out from the critical section. Now P2 is also interested. P2 is also interested to access this critical section, but let's say again P1 got the chance and it is accessing the critical section. Okay, now P2 thinks like, okay, now I'm going to get the chance. Again P1 executes that. That means there is no limit on the number of times P1 can access the critical section, right? So in this case, P2 will face starvation. In this case, P2 will face starvation. And if this is the case, in that case, you can say bounded waiting is not satisfied. Why dogs stop the horse for maintaining processes in the park is maintained? I will tell you how it is going to do that. So we have the questions. In the questions, it will be clear to you, Utkarsh, how one process is stopping another process or not allowing another process to access the critical section. It will be clear to you when we take the questions. Now understand this, bounded waiting will be satisfied only if, let's say, P1 executed 1 or 2 times or maybe 3 times, but after some time P2 is also getting the chance to access the critical section. Okay, if this is the case, we can say bounded waiting is satisfied. But if this is not the case, in that case P2 will face the starvation, so bounded waiting will not be satisfied. So if I'm proposing any synchronization solution, in that case these conditions, these are the mainly primary conditions: mutual exclusion and progress. These are the primary conditions. Bounded weighting and architectural neutral, these are, you can say, the secondary conditions. Main conditions are mutual exclusion and progress. This should not be neglected if you are proposing any synchronization solution. Okay, what is architectural neutral? That means whatever solution you are proposing, that should be platform independent. That should be platform independent. It should not be dependent on the platform. Okay, so let's say if you are proposing some hardware solution, so hardware is platform specific, that is machine specific. So in that case you cannot say that this solution is architectural neutral, because it is a hardware solution, it cannot be implemented on any machine. Got it? But if you are proposing a software solution, so clearly you can say that solution, that synchronization solution is architectural neutral. Is it clear? Is it clear, everyone? So these are the 4 conditions or 4 requirements of synchronization mechanisms. One is mutual exclusion, progress, bounded weighting, architectural neutrality. Now, now let's see these definitions so that you can make your notes also. So I have explained you the concept of all these 4 mechanisms. Now you can see the definition. Mutual exclusion: no two contending process should be simultaneously executing inside the critical section. That means only one process should be there at a time. Progress, the same thing. If one is not interested, then it should not stop other process to execute the critical section. That is progress. When starvation occur, when only one process is getting the chance again and again to execute the critical section and other process is not getting the chance. Okay, so in that case, that other process, or you can say P2 process, will face the starvation. Clear? So any process who is not getting the chance, in that case, that will face the starvation. Utkarsh. Bounded weighting, again, no process should have to wait forever to enter its critical section. If the process is waiting, keep on waiting, and it is not getting even a single chance to execute the critical section, then there is no bounded weighting. There is no bounded weighting. Architectural neutral, already explained you. Platform independent, that means all the software based solutions, all the software based synchronization solutions will be your architectural neutral, will be architectural neutral. Now we are going to see we have basically classified synchronization mechanisms into two types. One is your busy waiting solutions. So if you are proposing some solutions, either it will be in busy waiting or it is going to be in blocking. Blocking means without busy waiting. So let's see here. We have test and set log, that is having busy waiting. What is actually busy waiting? Let's understand through one example. Let's say there is one room, and we are having 2 persons standing outside the room. Okay, now carefully see this. One person, okay, is getting the chance to enter into this room. Fine, so now he is present here. Okay, but this person also wants to enter into this room, but it is allowing only one person to enter into this room. Okay, only one person at a time. So in this case, what will happen? This person is standing here and keep on knocking the door, like koi hai, open the door, you know, bar it is knocking the door again and again. So that is what? That is a busy waiting solution, because in this case it is going to waste the CPU cycles. So if any process is doing busy waiting, in that case it is going to waste some CPU cycles. That is not good for the performance. Clear? So this is what we have, busy waiting. Now you can replace this with process P1, you can replace with process P2. P1 is accessing this critical section and P2 is waiting here, and it is executing. Now you can think how we can have that kind of situation where P2 is, you know, keep on knocking the door. So in technical terms, you can see here, let's say you have one while loop, right? And let's say you have some turn variable, turn is equal to 0. Okay, now you have the critical section here, and let's say you have turn is equal to 1. Now carefully understand this. Let's say the turn value initially it is 1. So let's say P1 is executing first. P1 is executing first. What will happen? It will execute this while loop. Turn is equal to 0. Is 1 is equal to 0? No, it is false. So as you have semicolon here, it will become false. So P1 will get the chance to access the critical section. Is it clear so far? P1 will get the chance to access the critical section. Now let's say P2 arrives. P2 arrives. Now in that case, what will happen? Let's say after entering the critical section, let's say let's say it has turn is equal to 1 here. Let's suppose turn is equal to 1 is here before just critical section. So what it will do? Okay, turn is equal to 0, sorry. So it will update the value of turn is equal to 0. Now P2 arrives. P2 will also execute this while loop. Turn is equal to 0. 0 is equal to 0. Yes. So in that case, it is going to keep on executing this while loop. Why? Because it is going to act as an infinite loop. So until the turn value becomes 1 again, let's say you have turn is equal to 1 here. This process is going to keep on executing this while loop. So in this case, we can say this is a kind of busy waiting solution. Here it is going to waste some CPU cycles, and that is going to impact the performance of the system. Is it clear? This just I have taken random case. Through questions, it will be very clear to you how we are having busy waiting and all, and how we are going to check whether the conditions, the 3 conditions are satisfying or not: mutual exclusion, progress, and bounded waiting. Just let me know whether it is clear or not to you, everyone. And guys, do like the session and share as much as you can. Is it clear? So we have one busy waiting solution as test and set log, that we will see in the next class, and we have Peterson solution also, so we will see that also in upcoming classes. Let's talk about this blocking here. Now in case of blocking, what happens, which is without busy waiting? In this case, it is not going to keep on knocking the door. It is going to sleep. It is going to go on the sleeping mode. So if any process is executing the critical section, other process, if it sees okay, already one process is there in the critical section, in that case that process P2 is going to be in the waiting list. That is, it is going to sleep. Okay, it is not going to waste the CPU cycles. So that is what we call as blocking. So we have semaphore and we have monitors. Monitors is not there in the GATE syllabus. They don't ask any questions. If you check all the previous year paper, like from 2003 onwards, they have not asked even a single question based on monitors. So monitor is not there in the GATE syllabus, but just I have mentioned here that we have some blocking techniques, solutions, that is semaphore and monitors. Okay, is it clear, everyone? So now we have covered the concepts. It's time to solve the questions. And here you have the first question. So total 6 questions are there. Guys, start solving and let me know what should be the answer. What should be the answer for this question number 1? Yes guys, everyone. So concepts are done. Now we are going to solve these questions, and let me tell you one thing, these all are previous year questions. After solving, if you are solving these questions for the first time, you will get a lot of clarity on how to handle the synchronization questions, and these are GATE questions. Yes, everyone, what should be the answer? Shailesh is saying option C should be correct. Okay, Anu is saying option C. Okay, let's read the question here. A critical section is a program segment. Option A is which should run in a certain amount of time. No. Which avoids deadlocks. No. Where shared resources are accessed. Yes, this is the correct answer. So critical section is a section of code where we keep all the shared resources. So that is what we have is critical section, which must be enclosed by a pair of semaphores P and V. No, this is not correct. Clear? Let's answer this one now. Question number 2. Question number 2. When the result of a computation depends on the speed of the process involved, there is said to be what? Very easy question. If the result, final result depends on the order of execution of processes, that is nothing but your race condition. Race condition. B is the correct answer here. Clear? Very simple question. Now let's solve some tricky questions. If you are learning for the first time, then you are going to get much more clarity in this now. Yes, tell me what should be the answer. So here what you have to do in this question, you have to check mutual exclusion and you have to check progress. These two things you have to check whether it is satisfying or not. Whether it is satisfying or not. So let me read the question for you. Consider the methods used by processes P1 and P2 for accessing their critical sections whenever needed, as given below. The initial values of shared Boolean variables S1 and S2 are randomly assigned. As they are Boolean variables, so either it can take yes, Utkarsh. Why not B is correct in question 1? It is talking about critical section. What is critical section? Where we keep the shared resources. Okay. Now here if you see, S1 and S2 are Boolean variables. S1 and S2 are Boolean variables. So that means we have 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 cases. These are the 4 possible values here for S1 and S2. Now, which one of the following statements describe the properties achieved? So here we have to check for mutual exclusion and progress. In all the 4 options it is given. So this is the method used by process P1 and this is the method used by process P2. Yes. Okay, Shailesh is saying option A should be correct. You can take any case and try to verify whether mutual exclusion is satisfied or not. So first of all, focus on mutual exclusion. What is mutual exclusion? At a time, there should be only one process present in the critical section. So let's check whether mutual exclusion is there or not. Now if you see here, carefully see here, everyone, let's take the case of 0, 0. Let's take the case of 0, 0 when S1 is also 0 and S2 is also 0. Now, if S1 is 0, S2 is 0, let's say P1 is executing first. Let's assume. While S1 is equal to S2, 0 is equal to 0. This is true. This is true. As you have semicolon, so this will, P1 will be executing. P1 will keep on executing this. P1 will keep on executing this. It is not able to proceed. Now let's say P1 got preempted and now P2 is executing. S1 is not equal to S2. 0 is not equal to 0. This is false. This is false. So this loop will break. If this loop breaks, this P2 will get the chance to access the critical section. Now at this point of time, P2 is present in the critical section, but P1 is still busy doing busy waiting here. Is it clear? So now if you carefully see, mutual exclusion satisfied or not? Yes, it is satisfied. As you can see, at a time only one process is present in the critical section. Here P2 is present, P1 is not allowed to enter into the critical section. So mutual exclusion, yes, it is satisfying. You can compare these options also. Let's take this one. We have taken this one. Let's say 0, 1. Let's say 0, 1. Now if it is 0, 1, let's say P1 is executing again first. So 0, it is equal to 1, false. So in that case, P1 will access the critical section, correct? Now let's say P1 got preempted here. Now execute P2. 0 is not equal to 1, it is true. That means P2 will do busy waiting here. It is not able to proceed further. Again at a time, one process is present in the critical section, which is P1 in this case. So that means mutual exclusion is satisfied here. Sailesh, is it clear to you or not? Okay, you can take any case. You can take any case. You can take 1, 0. You can take 1, 1. Any these 4 cases you can take. You will find it out that mutual exclusion is satisfied here. If you have any doubt, guys, please ask. Clear na? All clear, everyone? Yes, Utkarsh, in case of P1 situation, ME is satisfied. In case of P1 situation, First situation you are saying now, in every situation it is satisfied, mutual exclusion is satisfied. Now let's talk about progress here. So in progress, understand this point, one process is not interested, so it should not stop other process to execute the critical section. If it is doing so, progress is not defined. Now let's consider this case only 0 0. Let's say P1 wants to execute, but P2 doesn't want to execute. Fine, P2 is not interested, but P1 is interested. So what will happen? 0 is equal to 0, it is true. So what will happen? P1 will do busy waiting here. That means P1 is not able to access the critical section. Yes. P2 is not interested. So that means P2 is not allowing P1 to access the critical section. Why I am saying so? Because it is P2 which is going to make S2 is equal to naught of S1. So if you are considering 0 0, that means this is S1, this is S2. It is a P2 only which is going to make S2 value as 1, and when it makes this value, then only P1 will get the chance, because 0 is equal to 1 will become false and P1 will be able to access the critical section. That means you can say P2 is not allowing, you can say P2 is not allowing P1 to access the critical section. Is it clear? Is it clear to all of you? Please let me know once, guys. Everyone. Clear? You can take any case. You can take this case also. All the cases. You can clearly see that one process is not allowing other process to access the critical section. Okay? So can we say progress is not satisfied here? Everyone? Can we say that? Even if you are getting a single case where progress is not satisfied, clearly you can say progress is not there. Okay? It's not like you have to check every case. If you find just even a single case where progress is not defined, progress is not there, clearly you can say this. Option A is the correct answer. Any doubt? Anyone? All clear? Okay, let's proceed this and let's see this question now. Solve this one, everyone. Question number 4. Solve this. Question number 4. And guys, do like the session. Share as much as you can. This is also a similar type of question, but let's try to solve it, because here it is talking about bounded waiting as well. Mutual exclusion, progress and bounded waiting. Yes, everyone, solve it. Total we have 6 questions. This is the 4th one. So we are going to increase the level also of the questions. I have arranged the questions in such a way so that you can practice first the basic questions and then the advanced questions also. What should be the answer for this one? Shailesh is saying option C. Okay. That means according to you this solution violates progress requirement. Progress is not there according to you. Okay. Anyone else getting the answer? Unstoppable, option A. Okay. That means this is a correct 2-process synchronization solution according to you. Fine. Anyone else? Now let's see here. Consider the following 2-process synchronization solution. The shared variable turn is initialized to 0 here. Turn is equal to 0 initially. Which one of the following is true here? So we have process 0 here, we have process 1 here. Fine. Let's execute. Let's start with process 0. Let's first find out whether mutual exclusion is present or not. So let's talk about mutual exclusion. Let's say process 0 is executing while turn is equal to 1. 0 is equal to 1. It is true or false? It is false. It is false. Colon, semicolon is there. That means this is going to become false and P0 will be able to enter into this critical section and execute it. Correct? Now let's say at this point of time P0 got preempted and now we are executing P1 process. again, while turn is equal to 0, initial value is 0, still it is 0, 0 is equal to 0, this is true, this is true. P1 will perform, P1 will do busy waiting here, it is not able to access the critical section. Can we say mutual exclusion is satisfied here? Yes or no? Everyone? Mutual exclusion is satisfied here. Okay. So mutual exclusion is satisfied because at a time only one process is accessing the critical section. So one thing we can clearly say that this solution violates mutual exclusion requirement. No, this is incorrect. This is incorrect. Clear? Clear so far? Let's talk about progress now. Let's talk about progress now. Let's see whether progress is satisfied or not. Now, let's say process 0 is executing or let's start with process P1. Let's start with process P1. Now, turn variable, initial value is 0 here. 0 is equal to 0, true. It is going to perform busy waiting. In progress, we always check that one process is not interested at all. So, assume that process P0, process 0 is not interested at all to access this critical section, but P1 is interested. So 0 is equal to 0. In that case, it is going to become true and it is going to perform busy waiting because semicolon is there, so it is not able to proceed further. So who is stopping this P1 process? Who is stopping this P1 process? Process P0 is stopping. How it is stopping it? Because it is the process P0 which is going to make the turn variable as 1. So if it makes the turn variable, let's say it is making 1, then only this condition will become false and P1 will be accessing the critical section. So can I say progress is not satisfied here? Everyone, can I say progress is not satisfied here? Because if P0 is not interested, P1 will not be able to access the critical section. So progress is not satisfied here. So is this a correct two-process synchronization solution? No. Why? Because progress is not satisfied. This solution violates progress requirement. Yes, it violates because progress is not there. So option C is definitely correct. But let's try to check bounded wait. Bounded waiting is there or not. So let's talk about bounded waiting. Now let's talk about bounded waiting. Turn is equal to 0. Fine. Now carefully see this. In case of bounded waiting, we see whether there is a limit on the number of times a process can access the critical section or not. So there is a limit or not. Let's find out. Let's say P0 starts first. Okay, starts first. 0 is equal to 1. False. This is false. Fine. It is there in the critical section. P0 is there in the critical section. Now, let's assume that turn is equal to 1. So it is going to make it 1. I'm sorry for it. Just a minute, guys. Yeah. So let's assume turn is equal to 1 now. It has executed this statement. Let's see process P0 again wants to access this, again wants to execute this. Process P1 is also interested, but process P0 is trying to access it again. Can it do that? No, it cannot do. Why? Because turn variable is 1 now. 1 is equal to 1. This is true. That means it is going to perform now busy waiting. It is going to perform busy waiting. Let's say process P1 tries to execute this. So turn is 1. 1 is equal to 0. It is false. So now P1 will get the chance to access the critical section. That means strict alternation. Exactly, Anu and Shailesh. Strict alternation is there. Strict alternation means first P0 is executing, then P1, then P0, then P1. So alternatively they are executing. Whenever there is strict alternation, clearly you can say bounded waiting is satisfied. Bounded waiting is satisfied here because strict alternation is there. So when strict alternation is there, yes, definitely bounded waiting will be satisfied. But now let me ask one question to you. Let's say if strict alternation is there, then can we have bounded waiting satisfied? Not in this case, just generally I'm asking. If strict alternation is not there, then can we have bounded waiting satisfied? Yes, tell me. Here strict alternation there, so that implies bounded waiting is there. Yes, tell me. If strict alternation is not there, then can we have bounded weighting satisfied? What do you say? Shailesh is saying false. That means if strict alternation is not there, bounded weighting is not satisfied. Let me tell you one thing. If strict alternation is there, definitely bounded weighting will be satisfied. But if it is not there, then also in some cases we can have bounded weighting satisfied. Then also we can have bounded weighting satisfied. Okay, is it clear? Okay. Now let's proceed to the next question. So option C is the correct answer. Option D is incorrect because bounded weighting is also satisfied here. Fine. Let's solve this question now. Second last question. Everyone, second last question. Okay, not always so false. Okay. Yes, solve this one. So here you have to check mutual exclusion. You have to check bounded weighting. You have to see a deadlock also in this case. So you have to verify these things. And strict alternation is there or not. Strict alternation is there or not. Now those who are confused, if strict alternation is not there, bounded weighting will be satisfied or not, that will be clear here. Okay, let me just move here. That will be clear in this question. Yes, what should be the answer, guys? Anyone getting the answer? First of all, check for mutual exclusion. You have to find the correct statement, true statement. Wants 1 and wants 2 are shared variables which are false here, initialized to false. Okay, Utkarsh is saying option C should be correct answer. Okay, let's see. Anyone else getting the answer? Yes, Shailesh, Anu, Noob. Noob is getting D as the answer. Okay. Let's see here. Let's solve this question now. Two processes P1, P2, both are initialized. Wants 1 and wants 2 are shared variable which are initialized to false. Let's write W1 false, W2 false. Fine. Which one of the following statement is true about the construct? Okay, so we have P1 process here, we have process P2 here, and we have to check all these things. So let's first talk about mutual exclusion. Let's say P1 wants to execute. Fine. So if while true, now you don't have semicolon, so it will be executing. It is a kind of infinite loop. While true, wants 1 is equal to true, so it will make itself true. This will be true now. Fine. While wants S2 is equal to true, this is false. So false is equal to true. False is equal to true. No, it is false. So that means process P1 will be there in the critical section. Clear? Process P1 will be there in the critical section. So far, now one process is there in the critical section. Now we are going to check whether other process is able to enter into the critical section or not. Let's see here. Let's say P2 is executing now. While true, fine. Wants S2 is equal to true. Okay. So let's make this as true. Now, while wants 1 is equal to true, wants 1 is true. True is equal to true. Yes, it is. Semicolon is there. Busy waiting will be there. P2 will perform busy waiting here. It will not be able to access the critical section. So can I say mutual exclusion is satisfied? Can I say mutual exclusion is satisfied? Yes, everyone. Okay. So mutual exclusion is satisfied here. Let's talk about bounded waiting. Now, in case of bounded waiting, both the processes are interested. Remember this point, because many students they get confused between progress and bounded waiting. In case of bounded waiting, both the processes will be interested to access the critical section. Then we have to check whether one process is getting starved or not. Okay, one process is facing starvation or not. Let's see this. P1 executes, fine. Wants 1 is equal to true, fine. Now wants S2 is equal to true. So initially it was false, we have made it true. True is equal to true, yes. So that means in this case, okay, wants to. So keep it as false. Initially, let's keep it as false. False is equal to true, false. P1 present here, fine. Now let's say P1 got preempted. Now P2 is also interested. How it can show the interest? It is going to execute this statement wants S2 is equal to true. So if it executes want S2 is equal to true, let's make it true here. W2, that is wants 2 is equal to true now, because P2 is showing its interest to access the critical section. Let's say it got preempted here. Now carefully say this. Let's say P1 is executing critical section and now wants S1 is equal to false. Okay, let's make it false now. Now remainder section, fine. Let's say P1 is trying to execute it again. P1 is again trying to execute it. Okay. So in this case, wants S1 is equal to true. Now, let's say before S1 is equal to true, P2 executes this while statement. So wants S1 is equal to true, it is false here. False is equal to true, false. That means as it was doing busy waiting, so it will get the chance to access the critical section. That means bounded waiting is not there. I mean, bounded waiting is satisfied in this case. Is it clear? Bounded waiting is satisfied in this case because now P2 was doing busy waiting here. So as soon as wants 1 become false, this condition false is equal to true become false and P2 will be present in the critical section. That means P2 is also getting the chance to access the critical section. So bounded waiting is satisfied here. Clear? Now let's talk about deadlock here. So carefully see this. Let's say P1 is executing wants 1 is equal to true. Let's make it true here. Now let's say P1 got preempted here. P2 is executing wants S2 is equal to true. Let's make it true. So both are true now. Now wants 1 is equal to true. True is equal to true. Busy waiting here. Let's come to here. Wants S2 is equal to true. True is equal to true. Busy waiting here. Now what will happen? Both are blocked. Now. That means none of the process is able to proceed further. So both are blocked, or you can say both are facing the system. The whole system is in deadlock now. So deadlock is there. Now we are having some doubts. Okay. How to know where to preempt? See, to understand this question and to solve this question, you have to think all the multiple perspectives. Okay, so with more and more practice, and if you see the code also, you will understand. So one by one, if you try to check the conditions, like mutual exclusion, let's say mutual exclusion. So you know, okay, one process you have to make it in the critical section, and then you have to check the other process, right? So how you can do that? Make it one process to the critical section and then check. Fine. Let's talk about bounded waiting. Now in case of bounded waiting, we know that both the processes are interested. So if P1 is interested, critical section, it is there in the critical section. Make P2 as also interested. So wants 1 is equal to true. That means it also wants to execute the critical section. So now P wants execute this statement wants 2 is equal to true. Then while is equal to, this will be doing busy waiting here because wants 1 is equal to true already. Now in this case, when it completely executes it, wants 1 is equal to false. As soon as it makes wants 1 is equal to false, this condition, this while condition for P2 will become false. Yes or no? this condition will become false. So in this case, P2 will be able to enter into the critical section. So that means bounded weighting is satisfied. But if you carefully observe here, strict alternation is not there. It is possible that P1 can execute. It is possible that P1 can execute again. Yes or no? Let's say P2 is not interested. So it's possible na ki P1 can execute again and again and again and again. So strict alternation is not there, but bounded weighting is satisfied in this case. Now if you have any doubt, anyone, please ask. Shailesh is saying, okay, P1 can enter in critical section any number of times, then how bounded weight is satisfied? This is the confusion most of the students they have. Carefully understand this point. In case of bounded weighting, always we have to make both the processes as interested. Fine? Because if you are not making P2 as interested, that means you are checking the progress, whether progress is there or not, whether P1 is able to access the critical section or not, again and again, right? But if you are checking bounded weighting, that means both the persons are interested to enter into the room, but one is getting the chance again and again. That is how we check the bounded weighting. But if other person is not interested and he is just standing outside, he is not waiting to enter into the critical section or in the room, in that case you are not checking bounded weighting, you are just checking the progress. Is it clear, Shailesh and everyone? This is the confusion most of the students they have. So in bounded weighting, both has to show the interest. Okay, then we check bounded weighting. Clear? Okay, so we can say deadlock is there because this will become true, preempt, that will become true. Both the while loops, both will be doing busy waiting here, deadlock is there. So let's see the options now. It does not ensure mutual exclusion. No, it ensures mutual exclusion. Incorrect. It does not ensure bounded weighting. Already proved here, bounded weighting is satisfied. Incorrect. It requires that process can enter the critical section. Strict alternation. No, strict alternation is not there. Okay, strict alternation is not there. P1 can execute again and again if P2 is not interested. Strict alternation means like P1 will be blocked. First P1 executes, now P1 will be able to access again when P2 executes that. So that is strict alternation. Okay, but here strict alternation is not mandatory, right? So here that is also correct. Incorrect. It does not prevent a deadlock. Yes, deadlock is there and it ensures, but it ensures mutual exclusion, because for deadlock one of the necessary condition is mutual exclusion. If mutual exclusion is there, then only there is possibility of deadlock. Clear? So mutual exclusion is there, deadlock it is there, so that means it is not preventing deadlock. Option D is the correct answer. Option D is the correct answer. Is it clear to all of you? Any doubt, anyone? Let's proceed to the next question now. The last question of today's class, and I want all of you to solve this correctly and quickly. So let me read the question for you. Two processes X and Y need to access a critical section. Fine, critical section is present here and there also. Consider the following two processes. This is process X, this is process Y. Now, if you see here, variable P and variable Q are shared variables and both are initialized to false. Clear? You have to check deadlock is there or not, mutual exclusion is there or not. Only these two things you have to check. So quickly do it. Both variables are false. Both variables are false initially. Tell me what should be the answer. स्टारवेशन कोई तभी तो फेस करेगा ना जब कोई भूखा होगा. इफ समवन इज हंग्री देन ओनली इट विल फेस स्टारवेशन, राइट? अगर मेरा पेट खाली नहीं है, मेरा पेट फुल है, सो आई विल नॉट फेस स्टारवेशन. सिंपल एज दैट, शैलेश एंड एवरीवन. ओके, दैट मीन्स आई हैव टू शो दैट आई एम हंग्री. ओके, एंड देन इफ आई एम नॉट गेटिंग द फूड, इन दैट केस आई विल फेस स्टारवेशन. As simple as that. Okay, let's solve this. Okay, Subrajit is saying deadlock is there. Okay, we'll see that. So let me write here also that var P is false initially and var Q is also false initially. Yes, now answer this. Yes, what should be the answer, guys? And you have to check two things here, deadlock and mutual exclusion. These two things you have to check here. Yes. Okay, let's solve this question now. Let's assume that process X is executing first. While true, fine, infinite loop. Var P is equal to true. Okay, let's make it true. Now let's first check mutual exclusion is there or not. Var Q is equal to true, false is equal to true, false is equal to true. No, it is false, but carefully observe there is no semicolon here. That means this is the complete loop here. Okay, if there had been any semicolon here, in that case it will be an infinite loop if it is true. But here var Q is equal to false, false is equal to true, that is false. That means process X will not be able to enter into the critical section. It will just directly jump outside, and then it will again execute while is equal to true. Okay, fine. Let's come to process Y. While true, fine. Var Q is equal to true. Let's make it true. Now, while var P is equal to true, yes, true. True is equal to true. This is true. That means critical section. Process Y is present in the critical section now. Okay. Now again check. Let's say it got preempted here. Now again we are checking whether process X is able to enter into the critical section or not. Now carefully see this. While true, var P is equal to true. Okay, already true here. Var Q is equal to true. True is equal to true. Yes. Now process X also present in the critical section. That means at the same time both the processes are present in the critical section. So what we can say, mutual exclusion is not satisfied, because in mutual exclusion no more than one process should be able to access the critical section simultaneously at the same time. Mutual exclusion is not satisfied in this case. There is no mutual exclusion. There is no mutual exclusion. Now let's talk about deadlock here. Let's say this is initially false, this is initially false. Okay, var P is equal to true, make it true. Let's say it got preempted here. Var Q is equal to true. Now var P is equal to true, yes, access the critical section. True, yes, access the critical section. That means if mutual exclusion is not there, deadlock cannot occur, because one of the necessary condition for this deadlock is mutual exclusion. But here you can see mutual exclusion is not present, so deadlock will never occur. Yes, that is correct. Deadlock will never occur. So here we can see the proposed solution prevents deadlock. Is it preventing deadlock? Yes, but fails to guarantee mutual exclusion. So option A is the correct answer here. Option semicolon is very important. Most of the students they commit mistake in this kind of questions. So deadlock, it is preventing deadlock because both the processes are able to proceed, and mutual exclusion is obviously not there because both the processes are accessing the critical section. So you can say overall this is not a correct synchronization solution also. Clear? अरे उत्कर्ष, डेडलॉक दोनों में होगा ना, एक सिर्फ P1 प्रोसेस में थोड़ी ना होगा, पूरे सिस्टम में होगा ना, दोनों प्रोसेस. बट हियर इन दिस केस डेडलॉक इज नॉट देयर because both the processes are getting the chance to access the critical section at the same time. So अगर mutual exclusion नहीं है तो deadlock भी नहीं होगा. Is it clear, everyone? I hope guys it is clear to you. So this is the Telegram link. You can just type in the search box CS_by_Anshul_Sir and you can join my Telegram group. After the session, I will be sharing the PDF and you can download it. You can make your notes, right? So guys, I hope you enjoyed it. So this was the first class, and do subscribe to Byjus Exam Prep YouTube channel, because a day after tomorrow, that means on 11th, we are going to have the next session. Yes, you have to improve your understanding. So we have the next session day after tomorrow, that is on 11th. Don't miss it, because we are going to discuss test and set lock. Okay, that is very important, and we are also going to solve some questions based on that. Thank you everyone for joining this class. We'll see you soon. Good night everyone, take care, and bye bye. Thank you all. Bye. Good night. वहाँ से obviously बंद करना।